Solving equations has always been a central topic in mathematics. Some are quite easy to solve, others not so much. Consider this function. Most conveniently, we can use the formula to find its two solutions. So what about this equation? It looks complicated, but after substituting t equal log 2 of x, we'll get a familiar equation. From here forward, we can proceed easily. However, consider this polynomial of degree 5. Mathematicians have proved that for polynomials of degree greater than 4, there is no general formula for their solutions. So, it is probably still manually solvable, but the process might be difficult and tedious. In these cases, analytical methods clearly fail. They are both annoying and common. So, what tools can we use? Do we have a numerical method? Let's play with this equation a bit. To approximate the root of any function, we need a process that will take us from a guess value closer to the root after each iteration. Look at the graph. With our naked eyes, we can immediately detect 3 roots at here, here, and there. Let's try pinning the root at 1.5. Let's start with a guess near it, say x equal 0.75. Draw a vertical line from that point so that it cuts our graph. Now, draw a tangent line at that point and mark the point where it crosses the x-axis. As you can see, this point is closer to the root. It is our new improved guess. Now, we repeat the process for several more times and we'll find that the last guess in line is very close to the actual root. And the intuition is just that. What we need to do now is to formalize the process and try to find a clear-cut formula. First, we need to take a random guess called xi. Now we need to find the tangent line of the graph at this point. As we're already familiar with finding the tangent line, here's the equation. Because we need to find the point where the tangent crosses the x-axis, we set the equation to 0. Rearrange and we arrive at the formula for the next and hopefully improved guess xi plus 1. We can now apply this formula to successfully find the I plus 1 guess until it is precise enough. You may ask, how much is precise enough? And there is no definitive answer. Usually, we need to define beforehand our stopping criterion by either evaluating the difference between two successive guesses or that the function at that guess is close to 0 at some precision points. What we have been doing is the Newton-Raphson method, named after the two famous mathematicians, Isaac Newton and Joseph Raphson. This method is popular for two reasons. First, for its simplicity, because it's based mostly on linear approximation, and second, for its rapid convergence. It usually takes only a few steps to hunt down the root. The Newton-Raphson method can also be used to find the approximate numerical value of irrational numbers. For example, the square root of 2 can be estimated to any desired precision point by solving the equation x squared minus 2 equals 0 using the Newton-Raphson method. Similarly for other irrational numbers. Powerful at it is, the Newton-Raphson method may still fail. When the function is not differentiable, the formula is inapplicable, and so the Newton-Raphson method can't be used. And even when the function is differentiable, problems may still arise. If the first derivative is really close to 0, the tangent line will be almost horizontal and will take it far away from the root. We may also encounter functions that trick the Newton-Raphson method and put it into a self-perpetuating oscillation, bouncing back and forth between 2 points and never converging to any root whatsoever. If the function had multiple roots, the guess may also not lead us to our desired root and instead steer to something else completely. So, now you know that the Newton-Raphson method is an incredibly powerful numerical method for finding roots. However, there are other methods that can solve the same problems while avoiding the pitfalls above. That said, the Newton-Raphson method is still very common because of its simplicity and speed. Thank you for listening.